In this lecture, we are going to be covering the properties of alkanes, how to name and draw alkenes, and then after that, we're going to be moving on to the alkynes. So, when it comes to alkanes, understand that alkanes have a variety of properties, specifically physical properties, that can be described in terms of their solubility and density. Understand that alkanes are more common than what we think. For example, solid alkanes can be found in the waxy coatings of fruits and vegetables. So for example, here we have apples that are very shiny, and that's because the waxy coating that they have. Peppers will be another example where we see these waxy coatings. Understand that these coatings are going to help retain moisture, inhibit mold, and enhance the appearance of fruit and vegetables. When it comes to solubility and density, as we already explained, alkanes are non-polar molecules, and that's the reason why they are insoluble in water. Remember, the rule of thumb in chemistry is like dissolves like. So since alkanes are non-polar, that's why they are insoluble in water, because water is a polar molecule. Now, when it comes to density, understand that alkanes are going to be less dense than water. They tend to be flammable in air, and we can find them in crude oil. So for example, the image that it is illustrated in this slide illustrates an oil spill in the ocean. The alkanes that are found in the crude oil do not mix with the water because of the difference in polarity. In addition, because they are less dense than water, they will float on top of it, forming a thin layer on the surface of the ocean water. As I mentioned in the previous slide, when it comes to alkanes, they are going to undergo a combustion reaction. And hopefully you remember when we introduced the types of reactions in chapter 7, combustion reactions is whenever you react a molecule, a compound with oxygen. Now, it happens to be that when we are reacting alkanes in a combustion reactions, the products are CO2, water, and energy always. It doesn't matter how large the alkane is, the products are always going to be CO2, water, and energy. The only thing that may change is going to be the moles of water or CO2 that you are going to be forming. So, as you may remember, when we were in the laboratory, methane is one of the natural gases that is utilized to cook, and it is what is in the gas line for the Bunsen burners. When we were utilizing it in the lab, we will form a flame because the energy that is exerted from the reaction is what makes the flame in the Bunsen burner. Now we are going to proceed to talk about alkenes and alkynes, which are the next two members for the hydrocarbon family. Now, understand that when it comes to alkenes and alkynes, alkenes are going to be molecules in which we have one or more carbon-carbon double bonds. When it comes to alkynes, these are going to be compounds that we have at least one or more carbon-carbon triple bonds. So, understand that we need a minimum of 2 carbons in the simplest forms of these functional groups. The general formulas for alkenes and alkynes are as follows. So, the general formula for an alkene is CnH2n, while the general formula for an alkyne is CnH2n minus 2. These type of functional groups within the hydrocarbon family are called unsaturated hydrocarbons because they do not contain the maximum number of hydrogen atoms that a carbon molecule can hold. Understand that we are going to see the reactivity later in this chapter. First, we are going to be discussing how to name alkenes. So, as I established in the beginning of this lecture series, understand that the first rule every time we deal with organic compounds and their functional group is going to be find the longest carbon chain of atoms. So, understand that when it comes to alkenes, that longest carbon chain needs to contain the carbon-carbon double bond. Once you have established that, understand that you can write the alkane name for the compound. So, for example, here, if we count the number of carbons, it's going to be 1, 2, 3, 4, 5. The alkane name for that compound is pentane. But because this is not an alkane but an alkene, then we are going to delete the ane and replace it with ene, which is the ending for an alkene. Then we are going to be numbering the carbon atoms starting from the end that is nearest the carbon-carbon double bond. Understand that when it comes to the priority in numbering, we are going to give it the lowest number to the carbon-carbon double bond. So that means that in the following structure, we are going to be numbering this molecule from left to right. And as you can see, that's the numbering for the compound. Now, as you can see, if the double bond is equidistant, in this term, equidistance means that it's going to have the same numbering in either direction for the carbon-carbon double bond. Then you will be, in order to break the tie, only then you will be beginning the numbering near the closest, you're going to start numbering near the end to the closest first substituent. Okay, that is not the case with the example that we have right now on the slides. Now, step 3, you need to indicate several positions in the system, and I'm going to be highlighting them. So you need to indicate the position of the double bond. That's the first thing that you need to do. And in addition, you need to be numbering also the location and the name for the substituents as a prefix to the name of the main chain. What does this mean? That in this case, the first word is pentene, which tells me that the longest carbon chain containing the carbon-carbon double bond has 5 carbon atoms. That's what the pentene means. Then the number 2 is for the location of the first carbon in the carbon-carbon double bond. Then in this system, which I'm going to be highlighting it in blue, we have, or in purple, this is going to be the substituent that is present. That substituent, as we learned previously, that is a methyl group. And that substituent is going to precede the name of the longest carbon chain and the location of the first carbon in the carbon-carbon double bond. So that's where the methyl comes from. So that is the name of substituent. And that number 4 before the name of the substituent is going to be location of substituent. When it comes to alkenes, similar to alkanes, we can have them in cyclic form. So cycloalkenes are going to have a double bond within the cyclic ring structure. Now, when we are naming cycloalkenes, understand that we are going to be assigning the double bond, the carbons 1 and 2, and when the substituent is present, understand that the priority we are going to give to the carbon-carbon double bond. If we only have one substituent, okay, understand that you need to give location for the substituent, but you do not need to include the location of the carbon-carbon double bond in the cyclic system, because it is always assumed that it is between 1 and 2. Let's practice now naming, given the structure, what will be the IUPAC name for several molecules that have alkenes. The rules that we discussed previously for alkanes, when we have multiple of the same substituent and different substituents in the molecule, also are applied to this functional group. So, as I discussed previously, we have to find first the longest carbon chain. In this molecule, you can select the molecule, the longest carbon chain that it is across. Another longest carbon chain that could be present, you could select this one. Regardless of the one that you select, it will give you the same answer. That's why both of them could be selected as the longest carbon chain. So I'm going to go with the first one. Then, if we have, as you can see, 4 carbons in a row, you can do this one of 2 ways. You can write the alkane name. You can say this is going to be butane. Then I'm going to erase the ane and place an ene. The other way to do is by simply saying this is 4 carbons. Because I have 4 carbons, then I'm going to use the prefix but. And because this is an alkene, I'm going to add ene at the end. Now, understand that once we have completed that, in this system, we're going to have 2 substituents. These substituents, I'm going to be highlighting them in purple. And we have 2 of the same. They are both methyl groups. And we have to number the longest carbon chain, in which this is carbon 1, carbon 2, carbon 3, carbon 4. If we do in this example left to right or right to left, it's going to give us the same numbering, which this is what I mentioned, what it means to be equidistant. If I number it left to right or right to left, as you can see, in any direction, the carbon-carbon double bond is going to be between 2 and 3. So that represents the whole idea of being equidistant. Now, understand that we have to give the location of the ene in this molecule. So when it comes to this, we need to place what is the location of the first carbon in this carbon-carbon double bond, and that's a 2. Remember that between words and numbers, we have to put a dash. And we also have to write the name of the substituent before all of that. So in this case, we're going to have methyl as our substituent. But because we have two of them, we're going to say this is dimethyl. Preceding the dimethyl, we need to give the location of the methyl groups. One is on carbon 2, the other one is on carbon 3. And remember that numbers and words are divided by a dash. Now I'm going to be proceeding to be doing the molecule on the left side in the bottom. Please remember to practice all of the problems and to double check your answers in the answer key that has been posted on the Canvas site for the course. Now, if you can see in this molecule, we can select the longest carbon chain first. And in this molecule, we can select this as the longest carbon chain. When we select this as the longest carbon chain, remember, we are going to be numbering this longest continuous chain that contains the carbon-carbon double bond in such a way that our carbon-carbon double bond is going to have the lowest number. So in this case, this is going to be carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. That means that because this is a carbon-carbon double bond, this is going to be pentene. The carbon-carbon double bond is between 1 and 2. That's why this is 1 pentene. Then we proceed to place the substituents. When it comes to this, I'm going to highlight the substituents in different colors. We have 2 CH3s and we have a CH2CH3. As hopefully you remember, a CH2CH3 is going to be an ethyl group, while CH3s are going to be methyl groups. So when we are incorporating this name, remember that we have to put these substituents in alphabetical order. So the one that is going to come alphabetically first is going to be ethyl. We give the location of that ethyl group, which is at position 3 in our longest carbon chain. Then we are going to give the position of my methyl groups. One is on 2, one is on 4, and since there's 2 of them, we're going to say dimethyl. For those students that are questioning that right now, well, D actually comes before E. Why would you put dimethyl after ethyl? Remember, and I'm just going to highlight it in brown, the prefix di or tri or tetra does not get alphabetized in naming. So that's why we have to place the dimethyl after the ethyl. Now I'm going to be doing at least one of the examples in which we are going to be looking at the given the name, can I draw the condensed and skeletal formula for these compounds? And I'm just going to do Roman numeral 1. So when it comes to 3-ethyl 1-pentene, and I have to do the condensed versus the skeletal formula, this is how we draw them. First, you always start building condensed or skeletal from the last word towards the first word. So if we look at the molecule, as you can see, we have pentene. Because of that prefix pent, I know that there are 5 carbons. So I'm going to write 5 carbons in a row. As you can see, that carbon-carbon double bond, because I have the number 1, that means that it's going to be between carbons 1 and 2. This molecule has 1 substituent on carbon 3. I am going to write the numbers on my longest carbon chain. This will be 1, this will be 2, 3, 4, 5. It is easier when you're drawing it to put it in a place that you can see it from left to right, just like we read in English. So, as you can see, 5 carbons in a row. On carbon 3, we have an ethyl group. Ethyl groups mean that we have a CH2 bonded to a CH3. And because we have a condensed structure, then we're going to be filling in each of the carbons with hydrogens until they have a complete octet. So carbon number 1, it has 2 bonds, so that means that it needs 2 more with hydrogen in order to complete its octet. Remember, CH2 is the same thing as H2C. That is just illustrating in terms of space that those hydrogens belong to that carbon. Carbon number 2, it has 3 bonds, so it only gets 1 hydrogen. Carbon number 3, it has 3 bonds, so it gets only 1 hydrogen. Carbon number 4, it has 2 bonds, so it will get 2 hydrogens. And the last carbon in the series, it only has 1 bond, so in order to fill its octet, we need to place 3 hydrogens. Now, when it comes to the carbon, when we're doing the skeletal structure for these molecules, understand that what we need to do is similar to how we have practiced for the alkanes. The minute that your writing utensil touches the paper, that is carbon 1. Our longest carbon chain has 4, so this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. We are going to write a double bond between carbon 1 and 2. Okay? And if this is carbon 1, this is 2, 3, 4, and 5. To illustrate that ethyl group coming off carbon 3, we're going to write 1 carbon, 2 carbons. So this is the skeletal structure for Roman numeral 1 in part H of our worksheet. Now we're going to proceed to be naming alkynes. The steps for alkanes and alkenes are going to be very similar when we are dealing with alkynes. As you can see, the first rule, similar to what I was expressing to you guys, is find the longest carbon chain of atoms. It has to be the longest continuous chain. Now, when it comes to an alkyne, because of the signature in the functional group, we are going to be finding within, or I should say, we are going to be finding the longest continuous chain that includes the carbon-carbon triple bond. You may write the alkane name, erase the ane, and put -ine, just because if we're dealing with alkynes, that's going to be the ending of the molecule. The other way to do it is to say, okay, this hex represents the number of carbons in my longest continuous chain that includes the carbon-carbon triple bond. So, understand that given this skeletal structure, this is carbon 1, 2, 3, 4, 5, and 6. Now, as you can see, we are going to be numbering the carbon atoms starting from the end that is nearest the triple bond. If the triple bond is equidistant from the two ends, you're going to begin from the end that is nearer to the closest first substituent. In this case, we do not have substituents, so we need to only give the priority to the carbon-carbon triple bond. But in general, when you're numbering, you have to do it from the end that is nearest the carbon-carbon triple bond, and only if you have equidistant. So this numbering is only specifically for equidistant alkynes. Then as you can see, you need to indicate the position of the first carbon in the carbon-carbon triple bond. And then you're going to be placing the number before the main chain name. Then you're going to be given the location and the name of the substituent as a prefix to the name of the main chain. In this case, we only have 6 carbons. This is an alkyne. We give the location of the first carbon in the carbon-carbon triple bond. So for this example, the name is 2-hexyne. Let's do some problems from our worksheet. I'm going to do the 2 problems on the top, so the first row that we have in the worksheet. So, as we have illustrated before, we're going to find the longest continuous chain. So we can go carbon 1, 2, 3, 4. Or we can go carbon 1, 2, 3, 4. Either way, you will get the same answer. So let me just illustrate it with the highlighted atoms that I did at first. So when it comes to this, my longest carbon chain is going to be 1, 2, 3, 4, because remember that I have to give the priority to the carbon-carbon triple bond. So I have 4 carbons. The prefix for 4 carbons is but, because this has a carbon-carbon triple bond, then it's going to have the ending -ine. Before the longest carbon chain, I have to determine what is the first number for the carbon in the carbon-carbon triple bond. So this is 1. Then as a prefix of all of this, I'm going to write the name of the substituent, which in this case we only have 1, and it's a methyl group. And then I'm going to write the location of that methyl group, which is on carbon 3. Let's proceed to the next molecule. Let's first find the longest carbon chain, which is going to be 1, 2, 3, 4, 5, 6. The numbering that I just did verbally does not represent the correct numbering for the molecule. I'm just counting carbon atoms. Now, if I do the correct numbering for this chain, remember that the carbon-carbon triple bond needs to have the lowest number. Starting from the first carbon, this is going to be carbon 1, 2, 3, 4, 5, 6. In a 6-carbon system, our prefix is hex. Because there's a carbon-carbon triple bond, is going to end in -ine. We have to give the location of the first carbon in the carbon-carbon triple bond. So there's a number 2. So this is 2-hexyne. That's our main chain. And in this example, we're going to have 1, 2, 3 substituents that are the same. They are CH3s. So that means that our substituent name is methyl. Because there are 3 of the same, we're going to say trimethyl. And preceding that, we're going to give the locations of those trimethyls. We have 2 methyls on 4 and 1 on carbon 5. Let's do an example in which, given the name, we have to draw the condensed and the skeletal formula. In order to do this, I am going to be doing Roman numeral 2. So, when it comes to the condensed structure, again, we're starting from the last word and we're working our way towards the beginning. So, butane means that we have 4 carbons in a row. The number 1 says that between carbons 1 and 2, we have a triple bond. Dimethyl means that we have 2 methyls. The locations for them is at carbon 3. So if this is carbon 1, carbon 2, carbon 3, carbon 4, on carbon 3, we're going to have one methyl and another methyl. Then, because we have a condensed structure, we are going to make sure that each one of the atoms in this molecule has a complete octet, meaning 4 bonds to carbon. So carbon 1 has 3 bonds, it only gets 1 hydrogen. Carbon 2 already has 4 bonds, it doesn't get any hydrogens. Carbon 3 already has 4 bonds, it does not get any hydrogens. And lastly, carbon 4 is going to be getting 3 hydrogens to complete the octet. When it comes to the skeletal formula for alkynes, understand that alkynes are going to be linear molecules, because as you can see, any of the carbons that are being held by that triple bond are going to have only 2 electron groups besides them. So whenever we're writing that carbon-carbon triple bond, we're going to be writing 3 lines. In essence, this is carbon 1 and this is carbon 2. When we are writing the rest of the molecule, understand that then carbon 3 is here, and then is when the bending happens. In this case, we only have 4 carbons, so this is going to be carbon 4. On carbon 3, we have methyl groups. When it comes to methyl groups, here's a methyl group, here is the second methyl group, and this is the structure for Roman numeral 2. The next section in chapter 11 has to do with cis and trans isomers. Previously, we already discussed what structural isomers is, or what structural isomers are. Structural isomers, remember, these are going to be, when you compare 2 molecules, they're going to have the same chemical formula, and they're going to have different attachment of the atoms. Cis and trans isomers are going to be specific to alkenes because of the presence of that double bond. Understand that because of that double bond and its rigidity, this bond does not rotate. And that's why we have cis and trans isomers. Now, this carbon-carbon double bond is going to be holding the atoms in fixed positions, and that's what gives rise to the cis and trans isomers. For example, we have the following molecule, which is 1,2-dichloroethene. In essence, because these compounds, we can have these 2 chlorines on the same side of the molecule, then we are going to utilize the word cis to symbolize that they are on the same side of the molecule, meaning that both of these chlorines are going to be on the upside. If they are both facing down, that also means same side. Now, again, if they are on the same side, then we use the word cis. If we look at a compound in which now, and then again, this is the trans isomer of this molecule. If the chlorines, as you can see, one is facing up, but the other one is facing down, that means that they are on opposite sides of that carbon-carbon double bond, and that's when we illustrate it by saying the word trans, okay? Now, I'm going to discuss in detail how to determine if something is cis versus trans. And I'm going to illustrate this by doing at least the first 2 molecules on the first row. Make sure that you practice with the rest of the molecules that we have in the worksheet. So when we are looking at a molecule and we're trying to determine cis and trans, understand that one of the best ways that we can do this is by redrawing the molecule and making sure that that carbon-carbon double bond is horizontal. So I'm going to redraw. So this squiggly line is my representation for redraw, and I'm going to redraw this molecule and I'm going to put it sideways, meaning that I'm going to have now the carbon-carbon double bond in a horizontal position. Now I'm going to be asking myself, looking at this compound, this carbon is going to have a hydrogen, this carbon is going to have a hydrogen. When we're trying to determine cis and trans in a molecule, in essence, we have to follow the following step. Step number 1, carbon-carbon double bond has to be placed horizontally. And that's why I had to redraw the molecule. Then you're going to divide the molecule in half. So as you can see, I'm going to cut through the carbon-carbon double bond. Then I'm going to look at the atoms that are bonded on either side of those carbons. So what I mean by that is that this carbon atom is bonded to a carbon here in the bottom and to a hydrogen on the top. So the third rule is going to be, which I'm going to write it up here, determine high priority atom versus low priority atom. How do I determine that? The high priority atom is going to have the highest atomic number. The lowest priority atom is going to have the lowest atomic number. So, looking at the molecule that I have, if I look on the left side of the molecule, this carbon atom is bonded to a hydrogen and is bonded to a carbon. When we look at the atomic number for them, we know that carbon has a higher atomic number compared to hydrogen. So this is going to be high priority and this is going to be low priority. Then let's move to the carbon on the other side. Here is the carbon atom that has been held by the carbon-carbon double bond. That is attached to a carbon that is right here and is attached to the hydrogen. So when we look at it, this carbon is bonded to hydrogen. This carbon is bonded to another carbon. So when we do the priority, understand that this is low priority, this is high priority. So what that means is that when now we look at the molecule, so the fourth and last step is look at the molecule from left to right, and if you have a cis arrangement, you're going to have low, low, high, high, as you can see in the example for the first one, or you're going to have both high priority groups in the top and both low priority groups in the bottom. If we have trans as an arrangement, then our highs and lows are going to be on opposite sides. So you're going to see low, high, high, low, or the opposite. high, low, low, high. Remember, this only applies to alkenes. So let's do one more example. So let's say that I have the second molecule. Again, in the second molecule, I'm going to turn it a little bit on the side. So visually, I'm not going to redraw it because of in terms of space, but understand that here, I'm going to first cut the molecule in half. Okay? In the first one, I had to redraw it because the carbon-carbon double bond was on the side. Then I'm going to look at the atoms that I have in the molecule. Here there's a carbon. 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 And those carbons have hydrogens. This one has 3. This one has 2. This one has 3. This one has 2. Now, we are going to look one side at a time. If we look at the left side first, we have a carbon atom bonded to carbon and then bonded to carbon. So at this point, there is no point of difference when we look at what is directly attached to that carbon atom. Because here we have a carbon and here we have a carbon. Now, the carbon on the top is bonded to 3 hydrogens, while the carbon in the bottom is bonded to 2 hydrogens and a carbon. So as you can see, if we now look at what is attached, carbon, carbon, hydrogen, 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 now we found a point of difference between the 2 substituents. So that means that this whole group in the bottom, the CH2, CH3, that's going to be the high priority group in this instance. So this is low priority group. This is high priority group. If we look on the other side, we are going to be comparing a carbon atom to a chlorine. Chlorine has a higher atomic number compared to carbon. So in this case, this is my high priority group. This is my low priority group. As I read this from left to right, as you can see, the arrangement is low, low, high, high. So both molecules, number 1 and number 2, are going to be cis arrangements for the alkenes.